All right, welcome back. Today we're going to talk about characteristics that are associated with the non-existence of a limit. So, in the past two videos, we've talked about the basics of what a limit is, and in those cases, we had solutions. But it turns out a lot of times, or not a lot of times, sometimes you will have a limit that fails to exist, and there are three basic characteristics that will cause a limit not to exist. And here they are at the top of the screen, bulleted there for you. So, what does that first one say? That first bullet point says the limit of f of x as x approaches c from the left is not equal to the limit of f of x as x approaches c from the right. So what is this telling us? This is telling us that the left limit not equal to the right limit. The limit from the left is not equal to the limit from the right. So it turns out, if that happens, then the overall limit, the two-sided limit, does not exist. Okay? Bullet point 2. If f, the function, increases or decreases without bound as x approaches c, or in the case of an infinite limit, as x approaches positive or negative infinity, then that means the limit does exist. Why? Now, why is bullet point 2 important? Or where does that come from? This comes from the fact that a limit must be a finite number. So if the y values are just increasing towards positive infinity or negative infinity, even though in some sense you could say that's a trend, like the y values just keep getting bigger, that's the trend. But a limit must be a finite number. And so if the y values are not approaching a finite number, well, that will cause a limit not to exist. And the last one is kind of weird. It doesn't happen, like, I'd say, in the wild very often. It only happens with specific types of functions, usually involving trig functions. But if a function oscillates very, 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 very quickly between two fixed values as x approaches c, then that will cause a limit to fail to exist. And again, this does not happen very often. It's almost always the first two bullet items that we're gonna see in our examples in this class, but we should be aware at least of the third bullet point, because that will happen on occasion with certain, usually with certain trig functions. Okay. Important note here: if a limit does not exist due to unbounded behavior toward positive or negative infinity, we will oftentimes write that the limit as x approaches c of f of x equals infinity, or maybe negative infinity. That is, if the y values are just keep getting bigger and bigger and bigger as x approaches c, we'll write that the limit equals infinity. Or if the y values get bigger and bigger and bigger towards negative infinity, we'll write that the limit equals negative infinity. However, it is very important that we understand such a statement is not claiming that the limit equals infinity. Why? Because the limit must be a finite number. Okay? A limit must be a finite number. Whenever we say a limit as x approaches c of f of x equals infinity, which we will say a lot of times when appropriate, if we say that, that's simply a special way of saying the limit does not exist due to unbounded behavior. I will say toward positive infinity in this case. Okay? So we will oftentimes say a limit equals infinity or equals negative infinity, but that's not claiming that the limit exists. It's just a notational thing that says, okay, the limit does not exist, in fact, due to unbounded behavior. Okay? A common mistake I see students make, first semester students make a lot of times, is to say a limit like equals two numbers, and that can't be a case either. A limit, if it exists, equals a single finite number. Okay, so a limit, if it exists, has to equal a single finite number. And now we'll look at a couple examples of where this doesn't happen. Okay, so let's see. Let's look at this function, absolute value of x over x. We will see this function several times this semester, so you might want to like file it away in your parent function section of your math brain. Remember, like your functions like x squared and x cubed and the cube root and absolute value, all that good stuff that you memorized in college algebra and maybe pre-calc. Add this to that list, because this will be a function that pops up and you'll want to know the graph whenever you see it. And it's actually, I guess it's very easy to recreate the graph if you forget it, but let's think about it. Like, okay, if you want to figure out the behavior of absolute value of x as x approaches 0, well, first of all, why are we even investigating the behavior as x approaches 0? Because if you think about the domain, 0 is not in the domain of this function. 0 is not in the domain. If you look at the domain of this function, it's what? It's all real numbers except for 0. Because you can't plug a 0 into that function. You get division by 0. But anything else is fine. 0 is the only trouble. Okay, so let's use a table of values to think about what's happening. And let's do this. So if you have, okay, plug in a -5, let's use this table of values. So if you plug in a -5, what do you get? You get absolute value of -5 over -5. So what's absolute value of -5? Well, that's +5. Then +5 over -5 is -1. And I think what you're going to see is, okay, that same answer is going to occur for any negative number you plug in. All right, just take a look. If you plug a -4 in, you get absolute value of -4 divided by -4. That's +4 over -4 equals -1. -3, same thing. Absolute value of -3 over -3, you get +3 over -3 equals -1. Okay, so in fact, you get -1 for all of the negative values you plug in. Now, clearly, you can't plug in a 0. We already talked about that. 0 is not a valid input. It's not in the domain. So we can say DNE right there. But now what happens if you plug in positive numbers? Okay, let's plug in a +1. If you do +1, it'd be absolute value of 1 over 1. Well, absolute value of 1 is 1. Divide by 1, you get 1. Okay, what about 2? Absolute value of 2 over 2, well, that's 2 over 2, which is 1. So what's going to happen for all of these y values, you get +1. By the way, a way to think about this algebraically is to remember the definition of absolute value. Let's consider actually we'll do that next. We'll do that next. I'll save that for after we get the answer, and we'll confirm our answer. Now let's graph these to get a graphical solution. -5, -1. There's a point right there. -4, -1. -3, -1. -2, -1. -1, -1. What does it look like is happening? There's a horizontal line. In fact, if we plugged in like -1/2 or negative, let's say 0.1. -0.1, you'd get absolute value of -0.1 over -0.1. And what would you get? Okay, absolute value makes the numerator positive. Oh, and I'm not sure why I put a negative sign there in that case. Let's see, erase. There we go. 0.1 over -0.1 gives us -1. So in fact, what we have here is a horizontal line at -1 that gets super, super, super close to the origin, or sorry, super close to the vertical axis, but it never touches that vertical axis, so we put a hole there. It's really, really close, but never touches. Same thing happens to the right, or an analogous thing happens to the right. We have the point 1, 1, 2, 1, 3, 1, 4, 1, 5, 1. And if you want to think about the behavior as we get close to 0, think about positive 0.1 over 0.1. Sorry, absolute value of 0.1. Well, the absolute value of 0.1 is just 0.1 divided by itself, you get 1. So in fact, what happens is, if you get really, really close to 0 from the right, all of the y values are just positive 1. And so the way we graph that is to put a hole there, and then we have our horizontal line extending indefinitely to the right. And now I think we can see that bullet point number 1 is coming into play here. Okay, we can see that if we consider the behavior from the left, that is, the limit as x approaches 0 from the left of absolute value of x over x, we can see that the trend is what? What is happening with the y values as we get really, really close to 0 from the left? Well, all of the y values, in fact, are -1. You can see that from the table or from the graph. Therefore, what's the trend? Going back to our informal definition, the trend is that the y values are equal, or the y values are trending at -1. And then we can look at the limit as x approaches 0 from the right of absolute value of x over x. And what's happening with the y values on the right? Well, again, from the table or from the graph, you can see that all of the y values on the right-hand side are positive 1. So clearly, the trend is positive 1. But what do we see is true about the limit from the left of 0 and the limit from the right of 0? Since they're not equal, that means the regular two-sided limit does not exist. So these two facts imply that the limit as x approaches 0, considering both sides, it's a weird looking x, let's fix that, does not exist. The limit as x approaches 0 from the left and the right does not exist. Now, here's what I see students do sometimes. I mentioned this a few minutes ago. I see students do this. They say, hey, well, the two-side limit does consider the left and right-hand behavior. So the limit equals plus and minus 1. However, that makes no sense because a limit has to be a single finite number. It can't be two numbers. I sympathize when some students say this because I understand what they're trying to say, but it's not mathematically correct. The limit cannot be two different numbers, and since the limit from the left and the right are approaching -1 and +1, and those are not the same number, we simply have to say the limit does not exist. Okay, so that's our probably most common reason. Actually, I don't know, that might be our second most common. It is a very common way that we'll see that a limit does not exist. So a limit does not exist if the behavior from the left and the right do not match. Okay, what's another limit or another reason that a limit might not exist? All right, let's look at the behavior of f as x approaches 0 and explain why the limit of 5 over x squared as x approaches 0 does not exist. Okay, Here's where knowing your parent graphs really comes in handy. So I said up here that, okay, add this function to your list of parent graphs. Well, okay, this one below it, you should know how to solve this one because of your knowledge of parent graphs. So specifically, the one I'm talking about is 1 over x squared. So f of x equals 1 over x squared. That's the parent graph of the reciprocal squared function. I mentioned it actually in one of the previous videos. It looks basically like this. Okay, basically like that. Okay. Now, how can we get from 1 over x squared to 5 over x squared? Well, also remember from college algebra that the way that what happens when you multiply, say, 1 over x squared by 5 is it scales the y values. So basically, you take all your y values and multiply by 5. Okay? What does that do graphically? Well, basically, graphically, that stretches the graph by a factor of 5. It doesn't really affect the shape of this particular graph too much because why? Well, it was already approaching infinity as we get really close to 0, and it's still going to approach infinity as we get really close to 0. But I guess we could say that, like, hey, for instance, on this graph, if you plug in a 1, you get the point 1 comma 1. That's easy. And if you plug in negative 1, you get 1 comma positive 1. If you plug that in a 5 instead, well, basically you would get this point right here. Sorry, if you plugged in, so 5 over x, you get 1 comma 5, and you would get negative 1 comma 5. So you get these 2 points. Now if you plug in 2, what would you get? You get 5 over 4. So if you plug in 2, that's what 5 over 4 is 1 1/4. So it's about like right there. Plug in negative 1, you get the same thing. So you would get, oh no, sorry, negative 2 rather. Same thing about right there. You know what? You plug in 3, 5 over 9. What's 5 over 9 approximately equal to? 5, oh, come on, 5 over 9 is approximately equal to about a half. Okay, so yeah, we could get a couple of values. And basically what we see is the graph is shooting up towards positive infinity as you get closer to 0. But then as you get further away from 0, the graph has this asymptotic behavior at the origin. And the graph ends up looking like this. So all we've done basically is scaled the parent graph by a factor of 5. And that's what we have. Not perfect, but you get the idea. Okay? Oh, did not mean to do that. Undo. There we go. Okay? So let's see. Now, how does this inform our limit discussion? Well, remember, a limit has to be a finite number. And what do we see as the behavior as we approach, say, 0 from the left of the function 5 over x squared, or perhaps the limit from the right of 0, indicated by a positive superscript of the function 5 over x squared. What do we see is happening in both those cases? Well, let's first look from the left. From the left, as we approach 0, on the x-axis, what's happening to the y values? They are shooting off towards infinity. So we say that the limit from the left is equal to infinity. Positive infinity, but infinity. Okay? Now, what about from the right? Well, from the right, as we approach the origin from the right, what's happening to the y values? Those y values are shooting off towards positive infinity again. Okay? So we say that the limit is equal to infinity. Now, do notice the limit from the left and the right are both equal to infinity. Now, that might seem weird because they are both equal to infinity, and so we then say that the limit as x approaches 0, just in general from the left and the right, of 5 over x squared is also equal to infinity. But please remember what we're saying here. In all three of these cases, this is just simply a special way to say each of those limits does not exist due to unbounded behavior toward infinity. So even though we're saying equals infinity, that's really just a notational convenience. We're saying that the limit does not exist, and here's why it does not exist. Okay, because remember, going up to our bullet list here for characteristics associated with the non-existence of a limit, if x increases or decreases without bound, that means the limit does not exist specifically. Okay, because a limit must be a finite number. So in this case, when we say the limit equals infinity, what we're saying is that here is the reason why the limit in fact does not exist. But we do like this notation because it allows us to be more specific. Like for instance, this example that we just started with, that limit does not exist because the left and right hand behavior are not equal. That's kind of like a regular does not exist. They just don't equal. They're not, the left and right are not equal to each other. However, the one below that, the left and right hand limits are equal, so that's not the problem. It's the fact that they are approaching an infinity, and that's unbounded behavior. That's the trouble. Okay, so we wouldn't want to put a D and E here, although these are basically special cases of D and E. Okay, so I'll put that. These are a special case of D and E, but we want to be more specific. So here, yes, the limit does not exist in each of these cases, but saying positive infinity says, okay, the limit does not exist, and here's why it does not exist. And that specificity is the good thing about this notation, is that it allows us to say why the limit does not exist, and it's due to unbounded behavior towards infinity in these cases. But just it's a little confusing at first because students think, oh, equals infinity, so the limit exists. But no, that's not what we're saying here, because a limit must be a finite number. Now, what was the third behavior that was associated with the non-existence of a limit? And this is the oscillation situation. So again, this is kind of a weird one. You don't see it very often, but here's an example of one. So discuss the behavior of f as x approaches 0, and explain why the limit as x approaches 0 sine 1 over x does not exist. Okay, so the graph is really weird. Like I would not expect you to know this graph. I wouldn't know it unless I have been teaching this for a long time. But it turns out if you graph this, what happens is you have basically a nice smooth curve to the right of the origin, to the left of the origin. Oh, that's not very much to the left. To the left of the origin's fine, but right at 0, this graph is crazy. Basically, it bounces back and forth between -1 and +1 infinite number of times. In fact, the closer you get to 0, the closer the faster it oscillates. Okay? So what does that mean? Well, this is that third example of when a limit fails to exist, and this is due to very quick oscillations. Now let's be very clear. We do lots of functions that oscillate. Sine looks like regular old sine, looks like this. It oscillates, but that does not cause any problems at all at the limit. Of course, you have your cosine, that looks, kind of like this. And again, that's a nice, gentle oscillation. No trouble at all with the limit. This is a very weird function that has trouble with the limit, and that's because these oscillations are so fast. So just to be clear, just because a function oscillates, that's not the problem. Here it's the problem that it oscillates so darn fast that that basically, a limit has to be a single finite number. But if the y values never like hone in on a specific finite number, well then you can't have a limit. The limit has to, there has to be a trend that the y values get really close to a specific y value. Well, here they're bouncing back and forth between -1 and +1, and so quickly there is no trend. So that's why we would say in this case that the limit as x approaches, in fact, left, right, or two-sided does not exist. So we could say 0 from the right of sine 1 over x, does not exist. And the same thing from the left. The limit as x approaches 0 from the left of sine 1 over x, does not exist. And then from the both sides, of course, that would have to be the logical conclusion that the limit from both sides also does not exist. We will not see this one very often, but it's something you need to be aware of. In fact, here, let me show you. Let me pull up Desmos. Desmos is a very nice graphing tool. We'll use it throughout the semester. Desmos.com. Here, let's show you real fast. Desmos.com. It's a very nice graphing calculator. Basically, it's what a TI should be as far as a graphing calculator. It actually makes nice graphs. It's not perfect, but it does make nice graphs. So sine 1 over x, and there is basically the same picture I had on my notes, but we can zoom in here. Okay, so notice it's even kind of like, notice as I zoom in, it's kind of acting crazy, because even this nice graphing calculator Desmos has trouble rendering this function. Now watch what happens as I zoom in here. I'm going to zoom in at 0. Now remember, there's no problem with the limit over here to the left of the origin or over here to the right of the origin. The only trouble with the limit is as you approach 0, so as you're really, really close to 0. And just watch what happens. As you zoom in, you can see that the oscillations are happening faster and faster and faster. I mean, it looks like we have just a solid mass here because those oscillations are happening back and forth between -1 and +1 so fast. That's what we mean by oscillations that cause a limit not to exist. Okay? So just a regular old sine function, regular old cosine function, not a problem. This crazy sine function, or you can do the same thing with cosine. Cosine 1 over x. Oh, if I could type it right. Cosine 1 over x. Same thing. Same crazy oscillations as you zoom in here. That function just oscillates faster and faster as you approach 0 from the left and the right, and this causes the limit not to exist. Okay. By the way, I encourage you to use Desmos all the time to graphically verify solutions. We will use this throughout the entire class. We'll get a solution by some analytic method maybe, or maybe a table method or something like that. And we'll say, hey, let's go verify our solution graphically. Developing a graphical intuition is a very important aspect of calculus. I will always have questions on a test or on an exam that have you analyze a graph, whether it's something that probably requires no calculations at all, just you looking at a graph and telling me something about the graph. Like here, looking at this, maybe this function, saying, hey, what's the limit? Or in the previous example, maybe I would give you this graph that I've drawn here and ask you what the limit is. So there will be several questions on the first test that ask you about evaluating a limit graphically. And that's, in fact, the topic of the next video. Or is it numerical next? One of those two is next. But both are important. But my point here is that graphical intuition is a very important part of calculus. And so it's important to always be checking your solutions graphically so you can so you can develop that intuition over the course of a semester. Okay, that's it for today. We'll take a look at our next section, and I'll see you then. Be sure to ask questions online or stop by the resources the college has for you. If you have any questions, you can always stop by my office or whatever. But there's lots of resources, academic support center, tutoring labs, et cetera, that you can get help if you need it. All right, until then, have a good one.